So the question we started with is, how does changing the angle, which changes the net force, affect the acceleration? And so during your experiment, you changed the angle so that you would get a new net force, and then using the motion encoder, you were able to determine the acceleration that net force would cause. So when your cart was released from the incline, the net force would be down the incline, and the acceleration would also be down the incline. So if you recorded the acceleration as being negative, then you should have recorded the force as also being negative. But we can simplify by just recording the magnitudes. So if we record the magnitude of the net force and the magnitude of the acceleration, you should get a graph of the net force on the x-axis, because that was what you were manipulating, and the acceleration on the y-axis. Your acceleration should be measured in meters per second squared, and the force should be measured in newtons. And then you plotted the data, and maybe the data looked like this, your data points, and you drew a best fit line because it looks like it's probably a line there, and we're able to then determine the slope. So if you didn't, put your data into a graphing calculator and let's get the slope of your best fit line. If you're doing this by hand, you would need to select 2 points on your hand-drawn best fit line and determine the slope based on the 2 points from the best fit line. Don't use your data points. So once you do that, you get an acceleration is equal to some slope value, and then the net force was on our x-axis, and then you'll have a plus, and this would be the initial acceleration, right? Because it would be the acceleration when the force is 0. Now the acceleration when the force is 0, well, that should be about 0 because it should be very small. So now what does this slope represent? Now the unit for your slope, let's see, check that. The unit would be the meters per second squared divided by newtons. Now a slope is usually a constant, something you didn't change in your experiment, something that you kept constant the whole time. And your slope value, I'm guessing, is approximately, if you graphed your acceleration on the vertical axis, is about 3. And this would be in meters per second squared times Newton. So what does it represent? What is this value that you got, which was about 3? Now, if you graphed your force on the vertical axis and your acceleration on the horizontal axis, your slope is probably about 0.3 in that range. So, but what does this number represent? Again, the slope is constant, and the slope should represent something that was constant about our experiment. So the thing that you kept constant, that you did not change at all, was the mass of the cart. So the mass of the cart was something that was constant in your experiment. Now the mass of the cart is about 334 or so grams. Now let's look at the relationship that we know about the gravitational force. So the gravitational force we determined was the mass of the object times the gravitational constant. And I was very specific and said that this gravitational constant, which was about 10, was measured in newtons per kilogram. Now, it's obvious that this about 10 is equivalent to our g, that was our acceleration due to the gravitational field. And acceleration is measured in the unit meter per second squared. So it's reasonable to make the connection that a newton per kilogram should be equivalent to a meter per second squared. That means that a newton would be equal to kilogram meter per second squared is a newton. All right, so let's go way back up here to our slope value. And so we can substitute what a newton is into this unit. So we'll have meters divided by second squared times kilogram meter per second squared, which would be equal to meters per second squared times second squared divided by kilogram meters. And then I can cancel out meter and a second squared and a second squared, and I get 1 over kilogram. And since 1 over kilogram would be the unit for 1 divided by mass, it seems that the meaning of this slope is 1 divided by mass. So let's go back and look at our equation again, where we had the acceleration was equal to about 3 net force plus what should be about 0 for the initial acceleration. That's the acceleration when the net force is 0. So this 3 represents 1 divided by mass, which is the inverse of mass. And let's take our number. Let's say 3 is equal to 1 over mass. Therefore, mass is about 0.333, and that would be in kilograms. And so converting that to grams, we'd have 333 or so grams, which is very close to being the mass of the cart. So that means we can write this more generally as the acceleration is equal to 1 divided by the mass. And I'm writing out the word mass because m looks like slope, and we've done a lot of slope here. So then this acceleration is equal to the net force divided by mass. And we could also write that as being the acceleration is equal to the net force divided by m representing mass, which would then give us that the net force is equal to ma. And this is known as Newton's second law. So now when we have situations in which the forces are unbalanced, instead of setting the forces equal to 0 because they're unbalanced, they cannot be equal to 0, we'll sum our forces and set them equal to ma. So sum the forces and set them equal to ma. And when the forces are balanced, the acceleration is 0. So really, the law of equilibrium, when the net force is equal to 0, is just a special case of the second law here, that when the acceleration is equal to 0, which means that the velocity could be 0 or the velocity could be constant. But when the force is unbalanced, so when they're not equal to 0, that means the acceleration is not equal to 0. And that would give us a net force then is equal to m times a. So now we'll sum our forces and set them equal to the acceleration.